Today, we are diving deep into the hidden world of logistics. You know, the logic that gets every single product you own, from your phone to your shoes, into your hands. It's this massive, incredibly complex puzzle, and for the companies that solve it best, well, the reward is literally billions of dollars.
Seriously, think about that for a second. That bag of coffee beans on the shelf, it didn't just teleport there. It was grown somewhere, roasted somewhere else, and then it had to be shipped. But how did the company decide which bags from which specific roasting plant should go to your local cafe? And more importantly, how did they figure out how to do it without going broke?
And here's the thing, this isn't just about coffee. It's about everything. Cars, computers, you name it. They're all part of this super intricate web of supply and demand. If you get it right, you save millions. But if you get it wrong, it can be an absolute disaster. So how do the pros actually solve this thing? Here's our game plan.
All right, first up, we're going to define what this logistics puzzle really is. Then, we'll actually map out the problem so we can see it. From there, we'll explore 3 different ways to solve it. A good way, a better way, and maybe even the best way. And finally, we'll see how this same thinking applies to a totally different kind of problem before we wrap it all up.
So what exactly is this puzzle that companies are spending so much time and money trying to solve? Well, at its core, it's what the experts call a transportation problem.
Okay, I know, that sounds pretty academic, but the idea behind it is incredibly powerful. It's basically a mathematical way to find the absolute best shipping plan. The sources, those are your factories. The destinations, those are the stores. And the whole point of the exercise? To do it all at the minimum possible cost.
Let's just boil it down. You've got a certain number of things at your factories. That's your supply. And you need a certain number of those things at your stores. That's your demand. The goal is just to connect the dots, to get everything where it needs to be for the lowest price imaginable. Simple to say, right? But way, way more complex to actually pull off.
So how do you even start to wrap your head around a problem this big? You can't just wing it. You need a map. And in the world of logistics, that map is something called a transportation table.
Let's look at an example from our source material. This is the SAO company. They've got 3 plants, A, B, and C, and each one can supply a certain amount of stuff. They need to ship all that stuff to 4 different places, X, Y, W, and Z, which each have their own demand. Think of this cable as our game board. The rows are where things are coming from, and the columns are where they need to go.
Okay, now the map gets really interesting. See all those little numbers? Each one is the cost, in this case in Nigerian Naira, to ship a single item from a plant to a destination. So for example, to get 1 unit from plant A to destination X, it costs 21 Naira. From plant B to destination Y, it costs 18. This grid of costs is the secret key to finding the cheapest possible plan.
Now, before we even think about solving this, there's one really critical rule we have to check. The whole thing has to be balanced. And that just means our total supply has to equal our total demand. In this case, we've got 160 units of supply, and we've got 160 units of demand. Perfect match. If they didn't match, we'd have to do some tricks to make it work, but for our example, we're balanced and ready to rock. All right, so we've got our map, we know our goal. Now for the big question, how do we find the best route? We're going to check out 3 different methods, and they go from being pretty simple and kind of dumb to progressively smarter. Let's call them good, better, and best. So our first strategy is called the northwest corner rule. It's popular because it's just so simple. You literally start at the top left cell, the northwest one, and you shove as many units in there as you possibly can. Then you just move to the next open cell and do it again. But what's its biggest flaw? It completely, totally ignores all those shipping costs we just looked at. It's easy, for sure, but it's not very smart.
And what's the result of that super simple approach? For the SAO company, the total cost comes out to 3,470 Naira. So this is our starting point, our baseline. It's a solution, yeah, everybody gets what they ordered, but is it the cheapest solution? Probably not.
Okay, time for a much smarter strategy, the least cost method. Now the logic here just makes more sense. Instead of starting in some random corner, you look at the entire board and you find the absolute cheapest route available, period. You fill that one up, then you find the next cheapest route, and you just keep going. This method actually pays attention to the costs, which is, the whole point.
And bam, look at that. This really shows you the power of just a little bit of better logic. By focusing on the cheapest routes first, the least cost method gives us a total cost of 3,350 Naira. That's a savings of 120 Naira over the first method just from using a better algorithm. Pretty good, right? But can we do even better? And that brings us to the most sophisticated approach, Vogel's approximation method, or VAM for short. Now, this one is really clever. Instead of just looking for the cheapest route, it calculates what's called a penalty for every row and every column. And that penalty is basically the cost of having to take your second best option. VAM finds for that penalty is highest, the place where a bad choice would hurt the most, and it solves that part of the puzzle first.
Now, for our specific SAO company problem, VAM actually gives us the same result as the least cost method, 3,350 naira. And while it didn't do better in this one case, what the source material points out is that VAM often gives you the best starting solution. Its logic is all about preventing the biggest possible mistakes, which makes it a really powerful tool.
So let's just put it all together. This chart tells the whole story. We started with the simple, blind northwest corner rule, and we got a high cost. Then we switched to smarter methods that actually looked at the costs, like LCM and VAM, and boom, the cost dropped immediately. This is what optimization is all about. A better strategy gets you a better result.
Now, this whole idea of finding the least cost or best fit is incredibly useful. And it's not just for shipping boxes from a warehouse. Let's see how this same logic applies to a different but very related puzzle, the assignment problem.
So what's the difference? It's actually really simple. The transportation problem is all about moving lots of units. The assignment problem, on the other hand, is about making perfect one-to-one matches. So instead of shipping 50 boxes to a store, you're assigning one specific engineer to one specific task. The goal isn't just to get the job done, it's to find the absolute best person for each job.
So formally, it's about assigning agents to tasks to minimize the total time or the total cost. And the ironclad rule is that each agent can only do one task, and each task can only have one agent. You can almost think of it as a special version of the transportation problem where every single supply and every single demand is exactly one.
And to solve this kind of puzzle, people use a really cool algorithm called the Hungarian method. We're not going to get lost in the weeds here, but the big idea is that it works by figuring out the opportunity cost for every possible pairing and then juggling the numbers around until the absolute best set of one-to-one assignments just pops out. It's another awesome example of how a smart process can find the perfect needle in a haystack of possibilities.
Whew. Okay, so after that quick tour through the world of logistics and assignment puzzles, what are the big takeaways we should remember?
All right, so what have we learned? We've seen that getting stuff from factories to stores isn't random guesswork. It's a solvable puzzle called the transportation problem. We learned that the key is to have a map of your costs, and that choosing a smart strategy, like VAM, can save you real money over a simple one. And finally, we saw that this logic goes beyond just shipping and can help solve one-to-one challenges, like finding the perfect person for a job using something called the assignment problem.
At the end of the day, all of this is about one thing: making the absolute best choice when you have limited resources and a bunch of different options. So the last thing I'll leave you with is this. Now that you know the basics, where do you see these kinds of optimization puzzles in your own life? Whether it's planning the most efficient route for your errands or figuring out how to best spend your time, I bet you'll start seeing them everywhere.